Today we'll talk about another type of finite automata, which is basically known as non-deterministic finite automata. We can represent it as NFA, or we can abbreviate as NDFA. Now, we have already discussed in our previous lecture what is the deterministic finite automata. Now here we will see what is basically non-deterministic. From its name here, non-deterministic, it means it's not necessary to have a unique path. It may have or may not have a unique path for each input. And even here, it is not mandatory that we need to define for inputs. Non-deterministic finite automata is then further consists of two types. One is non-deterministic finite automata without epsilon or null move, and another one is with null move. Let's first start with without a null move. The term non-deterministic means that for a given state, okay, or for a given state and on an input symbol, there may exist either zero, maybe no path, maybe one path, or maybe many paths. Non-deterministic is a useful concept that has a great impact on the theory of computation. So far, and in the previous one, when we were talking about the DFA, there was basically a unique path from current state to the next state. When the machine is in the given state, it reads something, okay, the next input, we know the next state. In that case, it is basically determined, and we call it as the deterministic computation. Sometimes when we have more than one choices, that we are in the current state and we get an input, and it is possible we might go to one state or another state. So that is basically known as non-deterministic machine. In this case, you can see this is an example, a simple example of a non-deterministic. You are in Qi, okay, and when the input is A, you might lead to Qj, you might lead to Qk. A non-deterministic finite automata, NFA or NDFA, is of course non-deterministic because it's very obvious from the name, implying that machine can exist in more than one state at the same time. Transitions could be non-deterministic. Each transition function therefore map to basically a set of states. So let's talk about non-deterministic finite automata without an epsilon move. Okay, so in the case of the finite automata, which is a type of known as non-deterministic, there may exist many paths, either maybe zero or many paths for a specific input from a current state to the next state. It is very easy to construct NFA as compared to DFA. The reason is because here there is no restriction. There should be a unique path, and the path should be defined for each and every input. That's why it is more relaxed. So creating an NFA is easier as compared to creating a DFA. Every NFA is not a DFA, okay, because those NFAs in which, for example, in here, this is an NFA, because in Q0, if it is A, you might be in Q0 and you might move to Q1. So this type of NFA is not a DFA, but each NFA, you can translate it into the DFA. For the DFA, only one path for a specific input. In NFA, many paths, maybe zero or many paths. NFA is defined in the same way as DFA, but there are two exceptions. This is an important thing. What are the two exceptions? These are basically the two exceptions, that it contains multiple next states. Yani Q0, you can be at when the input is A, you might be in Q0, you might even move to Q1. And it contains empty, means even the null string is allowed, and even empty means maybe no path for B is defined. Why non-deterministic finite automata? Because designing an NFA is easier as compared to designing a DFA. Why? Because in the DFA there are more restrictions. However, in the NFA we have more freedom. This is an example of NFA without epsilon move. So here you can Q0, when you are in Q0, when it is A, you might be in Q0, you might be in Q1. And the same case for Q1, if it is B, you might be in Q1 and you might be in Q0. Keep this thing in your mind that in case of NFA, that configuration is not allowed. Why that configuration is not allowed? Because it's not mandatory If a language does not support a specific path, no need to define that particular path. So all these things are same, those 5 tuples, finite set of states, infinite input symbol, initial state, final state. Only the difference is basically in the transition function. Here what we have, the transition function is current state multiplied by the input, yani current state, and then the input will lead to 2 power q, yani multiple next states. So either all the states are final state, or maybe the final state is a subset of all the states. So here you can see this is an example of NFA containing 2 consecutive A's or 2 consecutive yani B's. So let's see, we are in 0. So if it is A, we might be in 0, we might be in A. So because of that, one of the reason is this. And in Q0, when you have B, you might be in Q0, you might be in 0, you might be in 2. So this is also a reason why it is an NFA. For for 1, a path of A is defined. However, the path of B is not defined. For 2, the path of B is defined. For the path of A is not defined. Okay. Note that some of states has empty transitions on. Yani for 1, there is empty transition for B. For 2, there is an empty transition for A. The empty transition on A or B. And some have multiple transition. For 0, there are multiple transition for A, and there are multiple transition for B. Why this is non-deterministic? Because when you are in Q0, okay, at A, you might be in Q0, you might go to Q1. And in Q1, the path for B is defined, the path for A is missing. So if we want to solve this one, here what are the states? Q is Q0, Q1, and Q2. Input is A comma B. Starting state is Q0. Final state is Q2. Okay. The transition functions are that here when I am in Q0, when it is A, so I might be in Q0, I might be in Q1. So if you remember last time when we were discussing, I told you it is impossible to have here yani more than one state. It will always be one. Even empty is not allowed. So in the same way, we can make a transition function. Now let's make a transition table. You have input A, input B, Q0 is our initial state, then Q1, then we have Q2. Q2 is basically the final state. In Q0, when it is A, we might be in Q0, we might be in Q1. In Q0, when it is B, we will be in Q0. Q1, when it is A, it is empty. When it is B, we will be in Q2. In Q2, when it is A, we will be in Q2. When it is B, we will be in Q2. So these are the basic yani, 2 things, especially this one and this one, which was previously not allowed in case of DFA. However, in the case of NFA, it is basically allowed. So for this particular example, in Q0, multiple paths are defined for A, and there is an empty transition for B for Q0. So this is the yani, finite set of states, input, initial, final, and this is basically the transition function for those yani, states and the input. In NFA, the important thing is that it is not allowed in case of NFA to have the dead configuration. So dead configuration is basically not allowed, while in DFA we have. So here you can see for A, state A, if it is A, we might be in A, and we might go to B. Here, there is no, path defined for B, so no need to make the dead end. You can fill this thing by yourself. Now, designing an NFA that accept a set of all strings over 0, 1, in which the third symbol from the right, okay? So from the right is maybe this one, and this one. So from the right, the third symbol is 0. So this is basically fixed. Here we have the freedom, which is 0 and 1. Here we have the freedom for 0 and 1. Here what we did, it is fixed. And in here, because it is third from the right, so here what we did, we can put a loop for zeros as well as 1. So this is basically an NFA. We don't need to make any sort of, trap. And even if there is no part defined for Q3, For 0 and 1, it is absolutely fine. We don't need to, and it's not mandatory to make it. Now, here is the comparative, you can see the comparison between the DFA as well as the NFA. Here you can see we have, it consists of any combinations of A's and B, excluding, empty. Empty is basically not allowed. So what we did here is that we have, here Q0, and for Q0, this is basically representing what? This is representing this particular thing. So as this is a DFA, so for both the state, either is it 0 or either Q0 or Q1, for both, we need to define for A as well as we need to define for the B. But in case of NFA, it's not mandatory. So the same concept we can, or the same regular expression can be represented by using this DFA, NFA. You can represent it by using this. You can represent it by using this. So this one is also an NFA as well as DFA. However, this is not the DFA. Why? In Q0, multiple paths are defined for the input A and B. Same is the case here, that in this case as well, this is an NFA, but it is not a DFA. However, if we will consider this particular example, this example is also an NFA as well as DFA. Now, the same regular expression example that we did in the last video. So you can see here what we have. This is basically the DFA for the regular expression, which is this one. Okay, so here the path for B was not supported in the start. So what we did, we actually make a trap. However, this is basically what? This is basically an NFA. Similarly, the one any string that end with B. So this is an example of a DFA, and this one is an example of an NFA. Here it says that containing basically A. So regular expression for this one is, here it is A plus B whole star, and here also A plus B whole star. When we need to make a DFA, for that, what we basically did is we converted that regular, expression as this. Those two regular expressions are equal. It's not mathematically equal. It is equal because this regular expression and this regular expression basically represents the same language. So this is basically the DFA for that regular expression, and this one is basically the NFA. Now, the following, we need to draw an NFA that accepts a set of all string over 0 and 1 with 1, 0, 1 as a substring. So 1, 0, 1, minimum length is 3. And here we have a loop for 0 and 1. Here we have a loop for 0 and 1. Here for, 1, multiple paths is defined. It can be in Q0 and it can move to Q1. In the below figure, which one is NFA, which one is DFA? In this case, you can see this is a DFA, and you can also call it as an NFA. However, this one is only the NFA. It is not a DFA. So this is a DFA as well as NFA. However, this is only an NFA. Now, these are some of the examples. You can solve it by yourself later on. Even in here, this case, you can see this is basically an NFA, but this is only a DFA. But this DFA, we cannot call it as an NFA. Why we cannot call it as an NFA? Because in this DFA, what we have a that configuration, and that configuration is basically not allowed in NFA. There are some important points that need to be considered. This slide is a very important one. Look, if a word belongs to a language, in case of DFA, if a word belongs to a language, there will be exactly one path, okay, that will end at final. In case of NFA, if a word belongs to a language, okay, there will be at least one path, because there is possibility you might have multiple paths. In this case, if a word does not belong to a language, so it means there will be exactly one path that will lead to the non-final state. In this case, if in the case of NFA, if a word does not belong to a language, then there is no path, because in NFA, it is not mandatory to define the path for all possible input. In case of DFA, for every state, every input signal, there will be exactly one transition. However, in NFA, for every state, every input signal might have even zero, or it might have more transitions. At the end, you can say that every DFA is an NFA except those DFAs in which we have a dead configuration. So those ones which we have a dead configuration, those are not yani the what I can say, those are not the NFAs, because in NFA dead configuration is not allowed. However, in the case of NFA, it may or may not be the DFA.